Welcome to Calculus. We conquer our fears and flex in the face of adversity. On this episode, Stevenson will demonstrate we know a function that passes the vertical line test is considered one-to-one. If a function is one-to-one, then its derivative is a unique value for each specific x value. In other words, all you need is a single x value to evaluate into your derivative to calculate the numerical derivative. However, a function that's not one-to-one has an equation that's made up of implicit functions. So it's functions inside of it. So if a function is not one-to-one, then its derivative is a unique value for each specific point. So in other words, you need an ordered pair to actually evaluate the numerical derivative. So let's talk about how do you actually find implicit differentiation. So hopefully you have this flow map in your notes. If not, you may want to take a moment and write it down. So essentially, how can you differentiate a function where you have both your x and y terms that can't be separated algebraically? So in other words, how do you differentiate implicitly? So the first step you want to do is you want to basically take the derivative on both sides with respect to x. Here's the big factor though. You have to use chain rule in order to create the dy dx terms. What you're going to then do in step 2 is you're going to collect all the terms that have dy dx in it to one side of the equation, move everything else to the other side equation. In step 3, you're going to factor out whatever your dy dx term is. Then in step 4, you're going to divide the dy dx by the quantity that's next to it on the other side. And in step 5, what you want to do then, if necessary, if the problem's asking you to evaluate your derivative, then you would do it in step 5. If the problem is just asking you just to find the derivative, then you would stop in step 4. Let's look at an example now of how we can apply the implicit differentiation process. So the first thing you're going to notice is that notice y is not just y to the power of 1, it's y squared. So I know it's going to be implicit because my y, or my function, is not solved for y. So what I want to do, step 1, is find the derivative of both sides. And you're going to differentiate with respect to x. Now, the thing to remember is whenever you have a y, you have to remember it's an implicit function. In other words, there's a function hidden inside of it. We just don't know what it is. So make a note. Whenever you do y, whenever you do the derivative of a y term, it will always be chain rule. So I'm going to take the derivative of y squared. So the derivative of y squared. So when you do this, apply the derivative like you normally would. So I would do power rule here. So 2y to the power of 1 times, now chain rule. So it's the derivative of the outside with the inside left alone times the derivative of the inside. So we're just going to call it dy dx. Remember, the y term inside has some function. We don't know what it is. We don't need to know what it is. That's the best part. All we're going to do is consider it its chain rule. Now, on the other side, I'm doing the derivative of x with respect to x, so it's just 1. See, so this is the derivative of y with respect to x. That's why dy dx. So there's your first step. Is take the derivative on both sides. And remember, whenever there's a y term, it's going to generate its own dy dx because that's going to account for the function inside. I know this seems very odd. Just write it down. We'll get along. It'll be okay. At this point now, I want to solve for dy dx because that's ultimately what the problem's asking me for. In order to solve for dy dx, I need to isolate it. So since this is the product, I'm going to divide. Now, there's nothing more to do. There's no factoring required. There's no more operations. So this is my answer. dy dx is 1 over 2y. Notice your derivatives for implicit functions are going to look a little odd to you. They're not things you're used to seeing. Also, I'm not plugging any numbers in. Why? It didn't tell me to do that. It just said find the derivative. It didn't say to evaluate. So I'm going to find my derivative here. So the first step is to find the derivative on both sides. So what is the actual derivative of x with respect to x? See how y is inside my sine function? So this is where my chain rule comes into play. My derivative of sine is cosine. And then the derivative of y with respect to x is just dy dx. There's my implicit value here. My next step is to solve for dy dx, so since it's being multiplied by cosine, I'm going to divide the cosine. There we go. We could rewrite this as secant because remember 1 over cosine is secant. I'm sure you already recognize this one is definitely going to be more challenging because we have 1, 2, 3 terms to deal with. Also, look at the structure. We have a sum here, which is nice because that means I can just do the derivatives individually. But do you see how that's a product? So I'm going to have to apply product rule. Another thing to notice is I have 2 separate y terms. That means they're going to each generate their own dy dx. So I am going to have to do some regrouping, just like it's outlined in the process. So let's begin. So all I did there was my setup. Now I'm going to do the derivative of the left side. Now on the left side, I do regular derivative of x cubed is 3x squared. Now there's no chain rule in this one because it's with respect to x. But here, this is an implicit function because y is in terms of some x. I just don't know what it is. So what we do is we do regular derivative of it using power rule, and then we multiply it by a dy dx. That accounts for the chain rule, in other words, that hidden implicit function inside my y term. Now over here is product rule. Be very, very careful with these. So I highly recommend, because there's a coefficient, put it out front. Now we're going to do product rule. So it's first times derivative of the second, so the derivative of y is going to be 1 dy dx, plus second y times the derivative of the first 1. Now from here, I'm going to distribute the 18. Now you may be wondering on the right side here, how come there isn't a dy dx? Well, because of product rule. The only time you're going to get a dy dx is when you take the derivative of y with respect to x. Now I'm noticing I have a dy dx on the left and on the right. So what I need to do is make a decision. I need to move one of these terms to the other side. It doesn't matter which way you go. I'm going to go ahead and move my dy dx on this 18x to the left, which means this 3x squared needs to go to the right. Now I want to factor out my dy dx. And in my last step, I'm going to take this entire quantity and divide it to the other side. This does simplify. If I factor a 3 out on the numerator and the denominator, 3 over 3 is 1, so this would reduce. However, you would be fine with this answer here that I'm pointing to.